With the emergence of innovative alternatives like geopolymers, concrete, or more accurately like its key ingredients, cement reigns supreme. Its history stretches back millennia. Concrete's strength lies in its composition. Cement, a fine powder typically made from limestone and clay, acts as a binder. When mixed with water, it undergoes a chemical reaction called hydration, forming a paste that coats the binds together. Aggregates like the sand, durable and versatile material capable of withstanding immense loads and harsh environmental conditions. Of construction materials is evolving. Geopolymers, a class of inorganic polymer that can utilize industrial byproducts, offer a more sustainable alternative in some instances. They can exhibit impressive strength, durability, and their production often result in a lower carbon footprint compared to traditional Portland cement. While geopolymers hold immense promise for a greener future, it's crucial to understand that concrete continues to play a vital and often irreplaceable role. It will establish product processes, widespread ability, cost effectiveness for many availability, application, and extensive knowledge base within the construction industry, meaning it remains the dominant force globally. Furthermore, ongoing research and innovation are making traditional concrete more sustainable through the use of supplementary cementitious materials and carbon capture technologies. Scientists and engineers are constantly pushing the boundaries of this material. We're seeing the development of self-healing concrete that can repair cracks, automatically previous concrete that allows water to drain through, reducing runoff, and even 3D printed concrete structure that offer new possibility in design and efficiency. And now, let's put our discussion to our main topic. What exactly are geopolymers? And how can they revolutionize the way we build? At their core, geopolymers are inorganic polymers that can be formed through an alkaline activation of aluminosilicate, rich source materials. Think of industrial byproducts like fly ash from coal power plants or slag from steel manufacturing. Even natural minerals like metakaolin. Instead of relying on high temperature calcination of limestone as in Portland cement production, geopolymers are synthesized through a chemical reaction at much lower temperature. This fundamental difference is where their environment advantage lies. But the benefits don't stop there. Geopolymers' strength comparable to or even exceeding offer superior resistance to fire, chemical attack, or even higher temperatures. So, how do geopolymers fit in the existing construction landscape? They aren't necessarily meant to entirely replace Portland cement overnight. Instead, they offer a complementary approach. Geopolymers can be used in a wide range of applications from precast concrete elements and bricks to repair mortars and even 3D printed structures. The integration of geopolymers alongside traditional cementitious materials allows for more sustainable resilience building practices. We can reduce our carbon footprints, utilize industrial waste streams, and create structures that are built to last. The journey towards widespread geopolymers adaptation is ongoing research. It's continuously refining their properties, optimizing product methods, and developing standardized testing procedures, but the potential is immense. Geopolymers represent a significant step towards a more sustainable and innovative future building constructions. And now, this is the most important part of our topic, the chemistry behind geopolymer utilization. The chemistry behind geopolymer formation is a fascinating process involving the alkaline activation of aluminum silicate precursor. These materials are rich in silicon and aluminum oxide, typically in an amorphous or semi-crystalline form. Common examples included are fly ash, a byproduct of coal combustion in power plants. Its composition varies depending on the type of coal burned. A ground granulated blast furnace slug, a byproduct or iron production, is rich in calcium, silica, alumina, and metakaolin produced by a thermal activation of kaolinite clay. This process increases its reactivity. And here's our alkaline activators. These are highly alkaline solutions typically composed of sodium hydroxide, potassium hydroxide, provide the necessary high pH environment. Sodium silicate or potassium silicate. These solutions provide soluble silica, which plays a crucial role in the polymerization process. Condensation. The key step involves the condensation of this dissolved silicate and aluminate species. This process forms three-dimensional polymeric structure through a formation of silicon oxygens and silicon oxygen and aluminum bonds. Releasing water as a byproduct, this is similar in principle to the polymerization reaction in organic chemistry, but here we are dealing with inorganic monomers. Hardening and curing. The final stage involves the continued polymerization and structural development of the geopolymer matrix, leading to the development of strength and other desired properties. This curing process can occur at ambient or slightly elevated temperatures, significantly lower than the high temperature required for Portland cement hydration. You can see a simplified representation of polymerization. While a precise stoichiometric equation is difficult to define due to the variable composition of the source materials and complexity of the polymerization process, the general idea involves the reaction of dissolved silicate and aluminate species to form a polymeric chain. Geopolymers form when aluminosilicate materials are mixed with highly alkaline solution, causing a silicon and aluminum to dissolve and then link together into a strong amorphous network. Alkaline metals from the solution helps bind the structure and balance chain charges. This process creates a hardened material with a less ordered structure than traditional cement. And this is my presentation about the geopolymer utilization and the role of cementitious material in building construction and the chemistry behind it. Thank you.